Welcome to Pre-Calculus Lesson 2.5, Solving Rational Functions and Graphing Rational Functions. In Part 1, we looked at solving rational functions. In Part 2, we're looking at graphing rational functions. The learning target is for you to be able to identify holes, vertical and horizontal asymptotes, as well as the new one, slant asymptotes of a rational function, to be able to graph the function, and to be able to describe the end behavior. Critical things from Algebra 2, and one thing that we're adding that should be new for most of you, is the slant asymptotes. Identifying vertical asymptotes. Vertical asymptotes occur when and holes. So the very first thing that we have to do is we must first factor both the numerator and the denominator as well. First factor the numerator and denominator. The next thing we do is we look to cancel any common factors. But before they go away, we have to remember that those factors that were in our denominator are a part of the function's domain restrictions, even if they are not part of the final function. So they actually create a hole. So if I had a factor of x minus a over a factor of x minus a, and on top I had an x minus b and an x minus c on bottom, then the factors of x minus a would cancel and there would be a hole at x equals a. We'd have to plug a in to find the height of that hole. Once we've reduced the function, we look at the denominator of the reduced function. Set the denominator of reduced function equal to 0 and solve. These give us our vertical asymptotes. So in this case, our reduced function would be x minus b over x minus c. We would have x minus c equal to 0. We would have a vertical asymptote at x equals c. And though you can't see it yet, you will when we get to some numerical examples. Identifying horizontal asymptotes. There are 3 cases for horizontal asymptotes. Case 1, the degree of the, well, first off, we have our function, just as in the last video, defined as a polynomial function p of x in the numerator, a polynomial function q of x in the denominator. Case 1, the degree of p of x is greater than the degree of q of x. So what we're saying is we have something like x to the 5th over x. Well, as I plug in 10, this is going to be substantially larger. As I plug in 100, this is going to be even more larger than this. As I plug in 1,000, even more larger. Or a negative 1,000, even more larger, but in a negative direction. In this case, we don't have to worry about the denominator ever becoming bigger or equal to the numerator. So we are going to have no horizontal asymptotes. Case 2. The degree of p of x, the numerator, is smaller than the degree of q of x. That would be more like something like this. A linear function in the numerator, a 5th degree polynomial in the denominator. Even if I plug in 100 here, this is going to be substantially larger than 99. If I put in 1,000,000 here, this is going to be substantially larger than this. And the larger the values of x, the larger this number is with relation to this, meaning that the number gets closer and closer and closer to 0. So we do have a horizontal asymptote at y equals 0. Case 3. The degree of the numerator p of x is equal to the degree of the numerator q of x, or the denominator, sorry. Degree of the numerator and the degree of the denominator are equal. In this case, there will be a horizontal asymptote at y equals the lead coefficient of p of x over the lead coefficient of q of x. Identifying the zeros. Once we've identified any holes and any vertical asymptotes, any horizontal asymptotes, we're going to take the remaining numerator of our simplified function and set it equal to 0. Set p of x equal to 0 once the function has been simplified. So in the case above, x equals a is not an x-intercept. We saw that we have a reduced function and x equals a is actually a hole. X equals b is a 0, an x-intercept. The newest concept, this should all be reviewed from Algebra 2. The newest concept, unless your teacher covered it last year, which most do not, is the slant asymptotes. If the degree of the numerator, p of x, is 1 greater than the degree of the denominator, q of x, for example, the numerator is a quadratic and the denominator is a linear function. Here my numerator is 1 degree higher than the degree of my denominator. Then a slant asymptote exists. And here's how we find it. The slant asymptote will have an equation of y equals q, the quotient of p of x divided by q of x without the remainder. We'll look at a numerical example of this in just a little bit. In the next video clip, I will go through the examples on how to graph each of these. Please stay tuned to the next clip to see examples on how to find the asymptotes, holes, intercepts, including the y-intercept, stating the domain and interval notation, which shouldn't be new, and describing the end behavior in limit notation for rational functions.